Welcome to UVU CS3060 Lecture 5.3, where we talk about the shortest remaining time first scheduler. Now this scheduler is pretty much the same as shortest job first, but in the shortest remaining time first scheduler, we now introduce you to a preemptive scheduler. The preemptive scheduler actually has a new value added to it. Now they're all packed in here because the slides aren't right, but let me go ahead and draw those times in here. The arrival time for process 1 is at 0, but the arrival time for process 2 is at time clock 1, and it has a burst time of 4. Then we have the arrival time of process 3 at 2. It has a burst time of 9. Process 4 arrives at 3 and has a burst time of 5. Now, in the shortest remaining time first, we're still interested in picking the shortest burst time, okay? And if we were if all these jobs arrived at the same time, clearly we would start with 4, then move on to 5, then go on to 8, and then go on to 9. But because we can preempt the job, the scheduler is actually going to look at the queue every time a preemption happens, as well as every time a CPU burst ends. And those interrupts can happen in two places, either when it's coming back from a wait, or when the process is interrupted and put back on the ready queue via a timer. We're going to assume that all preemptions are correct and that there isn't one particular event. This includes arrival time. Arrival time can indicate that a process came into the ready queue from the wait queue because of an interrupt. So perhaps process 1 was in the ready queue and there was no other jobs in the queue, but at time clock 1, an I/O interrupt happened and process 2 was put back into the ready queue. Well, that interrupt will cause everything to be reevaluated. So if we take a look here, process 1 starts at or arrives at time 0 and is able to run to the first interrupt or the first arrival time. When that first arrival time happens, process 1's burst has actually gone from 8 down to 7. So process 1 now has a burst time of 7, and process 2 comes in with a burst time of 4. Well, which one gets chosen first? Process 2 gets chosen first. Now at time 2, let's go ahead and put time 2 here. Time 2, process 3 comes in. Now process 1 has run one cycle, so it's got 3 left, and process 3 has 9. Which one's the shortest? Well, process 2 is, so process 2 continues to run. At time 3, job 4 gets to run. Now process 2 has executed one more time cycle, so it's down to 2, and process 4 shows up with a time of 5. Well, still, out of all 4 of these jobs, process 2 is the shortest, so process 2 gets to run to completion. Once process 2 runs to completion, it's down to 0 now, and once it's 0, you can go ahead and take process 2 off the list. Shortest remaining time first looks through the job and chooses the shortest one, process 4. Process 4 will run, we'll go ahead and get rid of those, we'll run till 10 milliseconds. So once process 4 has run for 10 milliseconds, we can now choose between process 1 and 3. Process 1 is obviously the shorter, and so we run that to 17 milliseconds, at which point process 1 is set to 0. And now we can take a look at the last process on the list, process 3, which will run to 26. And now we can go ahead and average the wait times. So remember that when we're dealing with wait times, we're talking about the process initialization minus the process completion. Okay? And so in this particular case, we have process 1. It runs for, it actually waits from 1 to 10. So we have here, its wait time is 10 minus 1, or this gap of 9 milliseconds, where process 1 waited to perform its operation. Okay, so that's its wait time there. Process 2 waited from its start time, which was 1, and it actually got to get on right, it actually got to execute right after its initialized time, so its wait time was 0. Process 3, on the other hand, process 3 was submitted at 2, but it started at 17. So 17 minus its initialization time, 2, gives us 15. And finally, we have the process 4. Process 4 first started at 5 here, or it started here, but was actually, or it was initialized at it initialized at 3, but actually started at 5, which actually gave it a wait time of 2. Now, probably an easier way to calculate wait time, because remember, wait time is the amount of time that a particular process has not been executing, is actually to so let's take this value here. We know that the wait time for process 1 was 9 milliseconds because it waited 9 milliseconds while it was interrupted. Well, an easier way to calculate that wait time is actually to take the terminate time. Take the terminate time of that particular process and subtract from it the burst length. In this case, for process 1, its terminate time was 17. Its burst length was 8. Its initial burst length was 8, which gives it a wait time of 9. So while this representation here is accurate, it's hard to calculate because process 1 might get interrupted several times. So if we just simply take the two values, the termination time of the process minus the burst time, we can actually get an accurate wait time. In any case, the average waiting time here is 6.5, which, if you take a look at shortest job first, which was 3, it is not as good as shortest job first, but it is certainly a whole bunch better than first come, first serve. So we found ourselves a fairly good middle ground here. One thing to consider, though, is of our 4 processes, we had 4 context switches. So this doesn't seem like much, but every time we add more context switches, we actually are spending more time not running regular CPU jobs or user space jobs. Now, both shortest job first and shortest runtime first are considered priority schedulers. Now, a priority scheduler is just simply taking a number and evaluating whether a job should rise in priority on the scheduler's list. The number in the case of shortest job first and shortest runtime first is the burst time. So when we calculate that burst time using exponential average, that decides the priority of that particular process. Now, we've eliminated, using this particular algorithm, we've eliminated the convoy effect, but now we introduce a new problem, which is called starvation. I want you to consider that situation where we have one long burst time, one job with one long burst time, and then many jobs with short burst times. In a shortest job first and shortest runtime first situation, those little jobs will be scheduled before the long job consistently, to the point where that long job may never get executed if the arrival time of the short jobs happen frequently. Job starvation is the primary problem with any priority scheduler, including shortest job first and shortest runtime first. Now, a solution to that is called aging. In the aging case, what we do is, as time progresses, we increase the priority of the process. So, for example, in the case of the exponential average formula, the exponential average formula can actually have a modified version where the length the job has been waiting is subtracted from the exponential average, causing its priority to increase. Thus, if it waits for too long, it will actually eventually have a higher priority than the short jobs and be able to execute. And so here is an example of priority scheduling. Now, again, the numbers are offset here, but we can have burst time 10, 1, 2, 1, 5, and we can give these processes priorities 3, 1, 4, 5, and 2. And what will happen is the priority scheduler will choose a particular job to run first depending on its priority. So process 2 will get to run to completion, followed by process 5. Process 5 will run to its completion, even though its burst time is longer than other burst times. In this particular case, we're setting static priorities on these particular jobs. And as long as we have these static priorities in place, they're going to determine which job gets run next, no matter the size. And you can see that it doesn't look like the shortest job first, but these priorities can be arbitrarily set for whatever purpose it needs to be. We can set them based on a user priority value, or the kernel can have some algorithm for determining that priority. This ends lecture 5.3, where we discuss the shortest remaining time first scheduler.